Hello friends, today we see the design of IC engine components and mainly we see the design of cylinder and cylinder liner. Here is a systematic diagram of IC engine component. We know that cylinder liner, piston, connecting rod, crankshaft, ball gearing mechanism. This is the main component of IC engine. Mainly we focus on cylinder and cylinder liner. As we know, the function of the cylinder and cylinder liner to retain the working fluid such as mixture of air and petrol in petrol engine and air and diesel in diesel engine. It will also guide the piston by the gas force. As we know that there is a thermal energy generated in this cylinder. So basically high temperature incurred in this cylinder combustion chamber. So cooling is necessary for the cylinder and cylinder liner. So there are two types of cooling generally we see in cylinders. Air cooling, generally in small engines air cooling is done, like scooters, in motorcycles we see fins are provided for the cooling purpose to increase the cooling area. And in the large engines we generally see the water cooling. So water jacket or total assembly of water jacket, liner, frame we generally see in the big engines, large engines. Now when we talking about the liner, there are two types of liner again, dry liner and wet liner. Dry liner means what actually? Whatever the cooling water, it is circulated around the cylinder, but it is not directly in contact. It is not directly in contact with the cylinder surface. But in the wet liner, whatever the outer surface of your liner, it is directly in contact with the cooling water. Now we see how to calculate the cylinder size, basically length and diameter. So this is the simple formula which we see in the IC engine also. The indicated power is equal to brake power upon efficiency. From this we basically calculate indicated power, and from indicated power we know that the formula for indicated power is indicated mean effective pressure into length of stroke into cross-sectional area of the cylinder into number of working stroke per minute, that is small n. So from this we can calculate the size of the cylinder, that is a cylinder bore and length. And generally we know that L by D ratio, it is in between, generally we assume 1.25 to 2. L means length of stroke and D is nothing but the bore diameter of cylinder, and if it is not mentioned we take it as 1.5. and again the length of cylinder, now the length of cylinder is always more than length of stroke, so generally it is taken as 15% more than the length of stroke, so it is 1.15 of the length of stroke. Here we see L is capital L is nothing but the length of cylinder, which is equal to 1.15 to the length of stroke. It is 15% more than the length of stroke. Now the next calculation, it is for the thickness of the cylinder wall. When we talking about the thickness of the cylinder wall, again we consider here it is a thin type cylinder, and again we apply the formula of thin cylinders to calculate the thickness. And we know that in the thin cylinders the circumferential stress, hoop stress, it is a major stress, main stress. So same formula we are implementing here to calculate the thickness. T is equal to PD by 2 sigma C. We know that P is nothing but maximum gas pressure inside the cylinder. D is nothing but the bore diameter. Sigma C, it is a permissible circumferential stress for the cylinder material. And as we know that generally grey cast iron material, it is used for cylinder or cylinder liner, and it is centrifugally cast. And or maybe for heavy duty applications we are using nickel carbon steel or maybe nickel chromium cast iron. Generally we use grey cast iron. So sigma C value, it is not given. If it is not given, generally we assume in between 35 to 100 Newton per mm square. And again maximum gas pressure, if it is not mentioned, it is taken as 10 times the indicated mean effective pressure. So it is 10 into PM, it is a mean effective pressure. Again one more thing that is we see, that is a capital C. C is nothing but the reboring allowance. Reboring allowance, it is generally depends on cylinder bore, and up to 75 mm diameter bore diameter it is 1.5, for 100 it is 2.5, and suppose this value is in between these two, then by linear interpolation we calculate the value of reboring allowance. Next thing, how to find the stresses in the cylinder wall. Almost it is similar to what we done in case of thin cylinder. Again we consider the equilibrium of forces, vertical forces. In the diagram A, see here, sigma c downward force, it is equal to whatever the upward force, sigma c into 2t is equal to p max into d, and from this we can write the formula for to calculate the sigma c. Sigma c is the circumferential stress. Next, it is the longitudinal stress on the cylinder wall thickness. So sigma L, again when we consider the area, again we equate the forces, what are the downward forces, and equate with the upward forces. Here the upward force is the P max, which will try to separate the component, and sigma L, it is the downward component. For P max, again it is a circular area, so that's why we consider P max, it is for the inner diameter. So here inner diameter is D, so P into D square. Again pi by 4 is there, so pi by 4 D square into P max, that is the upward force, and downward force again pi by 4 D naught square minus D square. So only this thickness which is really affect, or which is considered for longitudinal stress, so D naught square minus D square. So we equate both the area, pi by 4 get cancel, and when from this we can directly write sigma L is equal to P max into D square by D naught square minus D square. So in this way we calculate sigma C and sigma L, and as we know that both these stresses are right angle to each other, they are not on the same direction, they are perpendicular to each other. So from this formula we calculate the net stresses. Sigma C net means net circumferential stress is nothing but sigma C minus mu into sigma L, where mu is nothing but Poisson's ratio. Again net stress along the longitudinal direction, it is again sigma L minus mu into sigma C. So from these two correlations we can easily calculate the value of sigma C and sigma L for the net value. Now here we see the example. Now we see the example to calculate the thickness and what are the net stresses and appearance stresses in the cylinder wall. The cylinder of 4-stroke diesel engine having following specification. The bore diameter is given 150 mm. P max is given 3.5. Maximum gas pressure. Poisson's ratio is 0.25. Factor of safety is 5, and cylinder material is again grey cast iron, 200 Newton per mm square. Now from this we calculate the sigma C. It is sigma C is nothing but it is a tangential stress basically. So 200 by 5. So we get the 40 Newton per mm square. This is sigma C value. Again it is in between 35 to 100 Newton per mm square, which we see in the previous slide. Next is the reboring allowance. As we know the cylinder bore is given, the value is 150 mm. So from the table we get the value of C, it is 4. So from the formula we directly calculate the thickness of the cylinder wall, and we get the value, it is 10.56, or we can take the next value, it is 12. It is not Newton per mm square, so it is 12. We get the thickness 12 mm. So we put the values of sigma C, then C, P max, and bore diameter, and from this we calculate the thickness of the cylinder wall, and it is 10.56 we get, and we take the next value, integer value, it is 12 mm. Then we see the stresses in the cylinder wall. What are the appearance stresses we get? That is by the formula of the thin cylinder again. So we calculate sigma C, and when we put the P max value capital D, that is the cylinder bore diameter and the thickness value of cylinder, and we get the circumferential stress, it is 21.88 and it is less than 40 Newton per mm square again, and whatever the longitudinal stress, it is 10.13 Newton per mm square, and when we calculate the net stress, again we get 19.35 Newton per mm square, and by second correlation we get 4.66.